everybody to this edition of the Basic and Clinical Science Anesthetic course. My name is Andrea Coleman. I work in Uppsala, Sweden. I've been helping with this course for quite a few years now, and I have the pleasure of talking to you about anesthetic equipment, which is a little mystery sometimes. So what we're going to talk about today is the anesthesia workstation, the breathing systems, gas analyzers, invasive arterial pressure, pulse oximetry, and a bit about safety in the operating room, because electrical safety and fire in the OR have come and will probably continue to come in the European exam. So, if I ask you, how does a car work? Well, you'll probably get an answer that is a little bit like this. Yes, I put my key, the gas starts flowing, and then the car moves. And that is very abstract. But if I ask you, well, how does the ignition work? Or how do the pistons work? Or how do the transmission work? Then you'll be able to give me much more concrete descriptions of the process. And it is exactly the same with the anesthesia machine. If I ask you, how does the machine work? Well, it's a very complex process. But if I ask you, how do the vaporizers work? Or the breathing systems? Or the monitors? Then it's much easier to describe how do they work. And it doesn't matter if I give you this old machine this old machine Narcos Med from the 70s, or this very nice Macket machine, because the vaporizers, if you know how vaporizers work, you know the old and the new, and we'll go through them. If you know how the breathing circuits work, then it doesn't matter which machine you're working with that day. You know the concepts of how the individual parts work, and that's what we're going to go through. So, the anesthesia workstation starts by getting a mixture of gases into the machine. And these gases come from belong to three different categories. It can be the high pressure system, the intermediate pressure system, or the low pressure system. So what are the differences here? The high pressure system is if the gases are coming from cylinders. So high pressure cylinders. Then they undergo a pressure regulation and you get the intermediate pressure system. But if the gases are coming from pipelines, it is directly an intermediate pressure system. So as you see here, there is a pipeline supply. And then from the intermediate pressure system, it undergoes a second stage oxygen pressure regulator. And then the pressure is lower even more, so it can actually enter the machine. And then the low pressure system includes the flow meters, the vaporizers, and finally into the patient. So, for example, here you can see that into the machine, the gases can come from the two different systems. The pipelines, which is the intermediate pressure system, or the cylinders, which is the high pressure. So they undergo their pressure regulations, and then they go into the machine via the gas inlets. Then you have a pressure reduction to finally go into the flow meters, then the vaporizers, and then the common gas outlet. There are some machines in which the breathing system is actually included in the machine. And some machines that don't. And of course, something very important for the European diploma is that we don't include gray areas. So there won't be a question about if the breathing systems belong inside the machine or outside, because different machines have different things. But you need to know how the vaporizers work, because different machines use different vaporizers, but the concept is the same. And then, of course, it goes to the airway, the patient, there is remote monitoring, then you get the hospital information management system, and of course, when the gas starts going backwards, then you have the scavenger system. So we're going to look at everything in more detail. The high pressure system receives gas from the cylinders. So it includes the cylinders, its attachments, the valves, the pressure gauge, and the primary pressure regulator. It reduces the pressure from 4,000 to 1,400 kilopascals to about 310 to 420 kilopascals, which this is 3 to 4 atmospheres. And this is to protect the patient, the apparatus, and maintain a constant pressure. And just remember, the cylinders are not usually used. They are a safety feature, and safety features come a lot in the exam, but it is not what we usually use. What we usually use is the pipelines. But if we talk a little bit more about the cylinders, and things you need to know is that they are made of chrome molybdenum steel or carbon steel, and this has come in the exam previously, that the sizes are defined by water capacity in liters. And this is super important. The gases are stored in compressed gaseous form, and we will go deeper into this during the physics lecture. But the most important part of this slide is this one, that the gas content is the water capacity in liters multiplied by the pressure in bar. 1 bar, 1 atmosphere. And this is very important because in the exam, you are asked sometimes to do simple calculations, but a simple calculation can be the gas content of a cylinder that has a water capacity of X liters and a pressure of X bar, or they can give it to see if you know the conversions between millimeters of mercury or torr, and play a little bit with the equivalences. And then you need to do the multiplication to find the gas content. But there is an exception, of course, and it is that N2O and CO2 are liquefied gases under pressure. So the pressure remains constant because as soon as I take a little bit of gas out, then more liquid is gasified. And then I take a little bit more and then it's gasified. So it doesn't matter what pressure it's showing because it will always show maximum pressure because it's always gasified until there's nothing left. So the pressure remains constant until the cylinder is empty. And to know the capacity, you need to weigh them. That's the way. So in the exam, if they ask you about N2O and CO2, they're probably asking you about that. You know that you need to weigh the cylinders in order to know their gas content. About the intermediate pressure systems is the received gas from the hospital pipelines, 300 to 400 kilopascals. A thing you will notice in my lecture as well as the physics lecture is that I will put every single unit for pressure there is. And this is to force you to work a bit on the conversions because the exam does exactly the same. So the intermediate pressure system consists of the pipeline secure inlet connections, the gauges, indicators, a master switch, the oxygen pressure failure devices, oxygen flush, and then more regulators. If I tell you what's the most important thing in this slide, it is the oxygen flush. So in the exam, they can ask you, the oxygen flush belongs to the low pressure system, and that's false. It belongs to the intermediate pressure system. And then if they ask you how these connections are called, they're called Schrader probes. And each probe is unique to each gas, so you cannot put the wrong connections. So we're going to discuss briefly the safety devices to secure the oxygen delivery. So the first safety device we're going to talk about is the oxygen pressure failure system, also known as the fail-safe valve. So anesthesia workstation standards require that if the oxygen pressure is reduced, then that the delivered oxygen concentration at the common gas outlet cannot fall below 21%, because 21% is what we're used to breathing. So there are mechanical, pneumatical, and electronic cut-off devices that prevent this from happening. And they detect failure, this one, the fail-safe valve, it detects failure based on pressure and not flow. So still, if the concentration of N2O is high, I can get a hypoxic gas delivery. So in the exam, remember the fail-safe valve is based on pressure, not on flow. And how does it look like? Well, if this happens to you, you will hear a whistle. And in the exam, if they ask you about the Ritchie whistle, then you need to answer that it's over 7 seconds at over 60 decibels at 1 meter from the patient. So if you hear this very loud peep that lasts longer than 7 seconds at the close distance to the patient, it's most probably the Ritchie whistle and is the fail-safe valve. Then we have the anti-hypoxia devices to overcome the problem that we discussed just now. So these are additional regulation of the flow. So the flow is to remain constant even if there are fluctuations in the pipeline pressure. And what this does is this reduces the oxygen pressure to 14 pCAG, a new unit so that you train on them, and 26 pCAG for N2O. So what this does is that it lowers the pressures of both so that what goes into the patient does not have an oxygen concentration below 21%. And then you have the oxygen flash, which delivers 35 liters per minute directly from the pipeline or the cylinder. But you remember that I told you that the intermediate pressure system has a pressure of 3 to 4 atmospheres. So what's the most problem if you keep the oxygen flash for extended periods of time? Well, you can cause barotrauma. And of course, if you're using inhaled anesthetics, then if you're using your sevoflurane at 2%, but you put 35 liters per minute into that system, then that 2% will become very diluted. So another consequence of using the oxygen flash is that it can dilute the inhaled anesthetics. And this can be of importance if you're doing inhalation induction, a example. And this is a question that I see myself asking in the part 2 examination. And a typical question is, how did you do a gas induction? And well, you start describing the system, how you put the sevoflurane, and then the examiner can ask you, but what happens if you start using the oxygen flash? And then you need to tell about the consequences. Then we move into the low pressure systems. And this is a little bit more, close to home because it's what we're used to working every day. And it delivers gas from the flow meters via the vaporizers and into the patient. So these are all the components, and we're going to go through them. The flow meters, there are several types, and in modern machines, they are fully electronical, but in older machines, they are mechanical. And we need to know about it. And how often the rotameters, aka mechanical flow meters, come in the exam? A lot. And there is the phrase that you need to memorize. The phrase to memorize is this one, that they are constant pressure, variable orifice flow meters. And what does this mean? It means that the pressure coming here into the flow meter is constant. So this here into the flow meter is constant, but the orifice, do you see how it is increasing in diameter? So it is a variable orifice flow meter. So each one is calibrated for a particular gas. So I have one rotameter per gas. And how do you know that it's working? Well, there is a little bobbin inside, and if that bobbin is rotating, then it's working. And how good are these rotameters? Well, the accuracy is within 10% of the indicated flow. But then the question is, which flow? So what happens is that there are two types of flow that we'll discuss during the physics lecture, and it is the laminar flow and the turbulent flow. And of course, the accuracy when the flow is laminar is much better than when the flow is turbulent. So if the bobbin is rotating nicely, then you know you have your laminar flow. But if the bobbin starts jumping up and down, it it signifies that the flow has become turbulent, and then the accuracy is not that good. And then in the exam, in the oral examination, for example, if they ask you, well, tell me how rotameters work, and you know, the best is to draw during the part 2 examination, and then you need to, of course, tell them, where do you read the rotameters? Well, it depends on which model you have. If you have this model that is like the arrow model, then you read it on the top of the bobbin. And if it's the round bobbin, you read it on the middle. And then it's important to know that even if your machine does not have rotameters, you're using rotameters every day with your patients, especially in the recovery unit. Because when we connect oxygen through nasal cannula and move and, activate the flow so it goes oxygen to the patient, there is a little bobbin there. Those are little rotameters. So even if your machine doesn't have it, you're using it continuously. Then you have transitional or hybrid flow meters that works with a needle valve. So this is the activators. And then the flow can be generated without electrical power. So even if the machine dies, then you can still get gases through. And then you have the electronic flow meters. The gas flow is set, measured, and displayed all electronically. There is no manual valve, and this is still backed up with a basic oxygen delivery system in case the machine runs out of power. So in case the machine dies completely, even though it has the primary battery, the secondary battery, it doesn't matter. If it dies, you still have a basic O2 delivery system. But there is also flow meter safety that we need to talk about, because I've already told you it's one flow meter per gas, and you can only control one at a time. And then there is a protective barrier around the control that minimizes accidents. So in case that you stumble into the machine, there, for example, in here, there are these little plastic things that won't allow it to be manipulated. Then the tubes are made of leak-proof with neoprene washer, so-called O-rings, at both ends of the flow meter assembly, so that to prevent leaks. The bobbin needs to be visible throughout the whole length of the tube, and the tubes needs to have an anti-static coating. And one more thing, it's very important in which order the tubes are located. For example, if we look at this design, I have my outlet here. I start with oxygen, then air, and then N2O. If there is a leak, then the first gas that goes into the system is the first gas leaking. So this is not a good setup. And then if we look here below, if I start with N2O, then air, then O2, if there is a leak, it will leak N2O, and I won't have hypoxic mixtures because I will still be giving oxygen. So the most important thing is that the oxygen is the last flow meter before the patient. Now we're going to move into vaporizers. So the volatile anesthetics must be vaporized before being delivered to the patient. And the vaporizers are located between the flow meters and the common gas outlet. And during the inhaled anesthetic, you're going to learn more about the gases. But there are certain things you need to know about the physics of vaporization. So the vapor pressure depends on the agent's characteristics and temperature. Vaporization requires energy, and this results in heat loss. And we're going to talk about this in a moment. The temperature of the remaining liquid decreases unless you put some heat in the system. A liquid boiling point is the temperature at which its vapor pressure is equal to the atmospheric pressure. This is important for desflurane. And at higher altitudes, the boiling point decreases. So we're going to see the most simple vaporizer, the variable bypass vaporizer. If in the oral examination you ask to draw a vaporizer, you can start with this one. So because it's the oldest model and it's the most simple to explain how it works. You have your fresh gas flow and a valve. and you say, okay, 95% bypass the system and goes to the circuit to the patient, and 5% goes into the vaporizing chamber and gets fully saturated with whichever gases I want to put into the system, and then they join, and I have a final X percentage of gas into my system. So the final vapor concentration is controlled by using the flow splitting valve. It depends how much I want it to to go into the vaporizing chamber and join the system, and how much I want it to bypass. So this is the most simple model of vaporizer, very useful for part 2 examination. But then we started adding things, because you remember that I told you that you lose heat? Okay, we're going to talk about it. Then the variable bypass vaporizers got an update, and you have the draw over, in which the gases are at atmospheric pressure and are drawn through the vaporizing chamber by the inspiratory efforts of the patient. So the patient inspires and draws the gas. So of course it needs to be low resistance, so the patient doesn't have difficulty breathing in the gases. But the accuracy is low, because we don't know how deep the patient is breathing. So this is the basic model. And then it gets an upgrade, the plenum vaporizer, in which the inspired gases are at the higher than atmospheric pressure. It is high resistance vaporizer, so it doesn't work in spontaneous that the patient is breathing in. You need to actively put the gases in the system. But the benefit is that it's accurate in a wide range of flows, but also accurate in a wide range of temperatures, because it has this thing, which is a temperature compensator. So, as you know, I'm going through the system and going out, and it's losing heat. Well, this is compensating for the heat loss. It doesn't mean that it's heating actively. It just means that it's compensating for the loss, because that one that's heating actively is desflurane that we're going to see in a moment. And this can be used in altitude, because partial pressure of the volatile agent remains constant. So in the exam, if they ask you in the part 1, can a draw over vaporizer be used in altitude? No. You need to use a plenum. Does the plenum comes with a temperature compensator? True. It is true. Is it a low resistance vaporizer? No, it's false, because plenum is high resistance. So there is a wide range of questions I can ask you there. And then we arrived to desflurane, which has its own name. It's the Tech 6 vaporizer. And the problem here is that desflurane's boiling point is 23.5 degrees. And what's room temperature? Well, it's very close to 23.5 degrees. So I challenge you, go and open a bottle of desflurane in your hospitals, just not make sure that's not too much left, so it's not too costly, and put it, pour a bit. What will happen? It will boil, because it boils at room temperature. And something that is boiling is very unstable, and you cannot administer that to a patient. So what this vaporizer does is that it heats the desflurane to 39 degrees, and then it keeps it under a pressure of 194 kilopascals, or at around 2 atmospheres. So there is a continuous flow of desflurane vapor from the chamber to the fresh gas flow via valves. And so we have the heating, then it's put under pressure, and then I have valves that, just in case something happens, it will stop the flow. And here there is a shut-off valve activated by tilting the vaporizer. So we're going to talk about the safety features of the vaporizers and why this is important. I'll make a 30-second break to tell you a story. I was a young resident, and my boss says, go bring me up desflurane vaporizer from the other operating room. And I went, and I don't know if you have taken, but the ones for the dragger machine are big, and they weigh a good, 4 kilos. So I was there carrying my vaporizer in the elevator, and my boss found me and said, Coleman, what are you doing? I said, well, boss, I'm taking the vaporizer. He said, be glad it's a desflurane vaporizer, because it has an anti-tilting device. So what happens if you tilt a desflurane vaporizer, it closes and no gas can come into the chamber, out of the chamber into the circuit. But that's not true with all vaporizers. For example, some vaporizers have a special mode that's, you find it in the dragger vaporizers with a T here, and it's called anti-tilting. So if you tilt it, nothing happens. But I'm going to back a few slides, and what happens is, if you don't have a valve here, and you tilt this vaporizer, then the anesthetic gas will come into this part of the circuit. So it will, flow out. And when you connect it to the patient and you start using it, maybe you can give a sevoflurane concentration of 35%. So to avoid that, there are the anti-tilting mechanisms. Then there is an interlock mechanism. So if you have a machine that has two vaporizers, you can only use one at a time. And then there is a pin safety system to prevent filling the vaporizer with the wrong agent. Okay, enough of vaporizers. Now you know how they work. We have gone through the draw over, the plenum, and the TIC6, which are the most that they always come in the exam. TIC6 I've seen many, many times, both in the written exam and in the oral examination. And we're going to talk about the breathing systems. So the breathing system may consist of all of some of the face mask, the gas hoses, the connectors, the reservoir bag, the CO2 absorber, and the APL valve, very important, a valve to switch between control and spontaneous ventilation, and one-way valves to prevent rebreathing. This I won't explain in detail because this is memorizing. You need to know them for the exam. Because in the exam, both in part 1 and part 2, there are a lot of questions about breathing system, and they can ask you. For example, in part 2, a typical question is, choose 2 breathing systems and describe and compare them. So then, well, a good option would be the waters to and fro and the airs TPs, because they're very different, so you have a lot of comparison to do. Or in the written exam, they can ask you which works better in spontaneous ventilation, which one works better in controlled ventilation, and some special comments here, for example, which are better for doing children anesthesia, because then you have less dead space. So this you need to memorize for the exam. And this image is taken from Morgan's Anesthesia. And if you're wondering what's air TPs, I've never used this. Well, probably you have used it. In the ICU, when you put your patient that you're waiting from the ventilator and you just put a T-tube that they just get oxygen through one side and breathe out through the other, that's an air TPs Mapelson. So I assure you, you're using this every day. And in your anesthesia machines, the most common to find are the waters to and fro, which is a Mapelson C, and the buy-in circuit, which is a Mapelson D. But really, this comes every year. So what is the full circuit? Well, you have your fresh gas flow, the inspiratory valve, in the limb, so there is a valve, so it prevents that when you breathe out, it goes through this side. Then you have your Y piece, your expiratory limb, and of course the valve and the APL. So I'm circling here 2 times. Where is the APL? The APL is in the expiratory limb. And this is very important because we put it in the inspiratory limb and I close it, then the patients won't get anything. It has to be always in the expiratory limb. And this has come as true or false in the part 1 many times. And we're going to talk about absorption systems. So the fact that we take advantage of rebreathing, it's the purpose is to conserve heat and humidity. The CO2 is exhaled and must be eliminated to prevent hypercapnia. So soda lime is the most common absorbent. How much can it absorb? 23 liters of CO2 per 100 grams. And this is a tricky thing. What is the main component? Calcium hydroxide. Because soda lime, you start thinking sodium, and absolutely not. The main component is calcium hydroxide. So in the part 1, the main components you soda lime is carbon hydroxide. True. If it's sodium hydroxide, then it's false. The reaction produces heat, water, and calcium carbonate. And before, many years ago, barium hydroxide was used, but it produced fire, so it's no longer used. So the one you're going to get asked, they can ask you about barium hydroxide as a historical matter and what are the risks associated, which is fire. But about soda lime, they can ask you about the main components and the absorption capability, which is 23 liters per CO2 per 100 grams. Then we have the anesthetic gas analysis. So as a historical interest, there is the mass spectrometry and the Raman spectroscopy. They are not going to come in the exam more than as historical interest because they are not used anymore. And most anesthetic gases are measured by infrared absorption based on the Beer-Lambert law. So the absorption of infrared light passing through the solvent, in this case the gas, is proportional to the amount of the unknown gas. But there is a caveat here. This works for gases that are made of two different atoms. So it can have many atoms, but they need to be different. For example, CO2, you have carbon and oxygen, it works. Sevoflurane, it works. But O2, it's the same atom, it's twice, but it's the same. And N2, well, they don't absorb infrared light. So you cannot use the infrared gas analysis for oxygen and nitrogen. And this has come in the exam. And then there is also an exception, which is halothane. Halothane is not analyzed via infrared, it's analyzed via ultraviolet light. So in the exam, if they ask you the infrared gas analysis can be used to measure halothane, that's false. It's ultraviolet. Then this slide, you will get it. I suggest then later you take a pause during this slide and read it, because it talks about the galvanic cell, the paramagnetic analysis, and the polarographic electrode. And you need to know them by memory for the exam. But the paramagnetic analysis we're just briefly going to describe. So oxygen is non-polar. You cannot use infrared. But this, you can use a magnetic field. So the gas passes by a magnetic field, and by measuring how the magnetic field behaves, you can measure the amount of oxygen. And this requires a water trap, like the water traps we have in our anesthesia machines. And that's why if the water trap has become filled with water, then you get weird results in the machine, and then you need to change the tubes that are filled with water and the water trap. But this is one of the importances of the water trap and how oxygen is measured in our machines with the paramagnetic analysis. But please review the galvanic cell and the polarographic electrode before the exam. Okay, we're done with the gas analyzers, and we're going to move into the invasive arterial pressure. So, fluctuations of pressure cause a pulsation of a saline column. So you have the fluctuations here. So I put my artery in my hand. Then there is the sensor, and the sensor is measuring the pressure against the sensor. And this displaces an electromanometer diaphragm, which has a built-in strain gauge, and this uses the Wheatstone bridge principle. And if you're thinking the Wheatstone what? The Wheatstone bridge principle is used to convert one type, for example, a mechanical stimulus, to a number that you get in your monitor. And during the physics class, we're going to see exactly how it works. And the deformation leads to a change in resistance of the strain gauge, and this is sensed electronically, and then you can build waves. But the arterial waveform are made of several different waves of different frequencies. So you need an analysis to join everything up and give you those nice numbers you see on the screen. And that's done via the Fourier analysis. So the Fourier analysis, so as I told you, the waves is just not one wave, it's a complex of waves, and any complex waveform can be deconstructed from a number of simple sinusoidal waveforms, and then you obtain the frequency of each, then you join them together, and then for the arterial blood pressure, the fundamental is the pulse rate at the constant is the MAF. So this is what's needed for the analysis. Do you need to know this? I don't think this will come in the exam about this, the fundamental and the constant. I don't think so. It might, but the Fourier analysis, yes. So the question is, the Fourier analysis is the use to construct the mean arterial pressure curves. Yes, that's true. Or the diastolic curves. And that is true. But I don't think they will ask for these things. So if you want to save your brain space, I would just keep the Fourier analysis and don't memorize this. And the question too, why do we zero the transducer? Well, the thing is that if I put a cut here in my artery, I will get a pew flow of blood outside. So we have the atmospheric pressure surrounding us, and then we have this extra pressure. So when you're measuring the blood pressure, you are actually measuring the absolute pressure. And that tells me nothing. You know, if I need to learn that the pressure of my patient is 820, I don't know what that is. So what we have done to simplify the process is we tell the machine, first sense this environment, this you're feeling, which is the atmospheric pressure, that's 0. And then whatever you feel on top of that, then that's the value I want to know. So it doesn't matter if you're using your invasive arterial monitoring at sea level or high in the mountains, because by doing the 0, you are telling the transducer, this you're feeling right here, that is 0 millimeters of mercury. So it's a way to standardize the measuring and make it easier. There is something about arterial blood pressure that's called the damping, and the damping is the absorption of energy of the oscillations. So anything that reduces the energy will reduce the amplitude of the oscillations. But a little bit of damping is necessary in all systems, and that's called critical damping. But if you have too much damping, then it's called over damping, and you get these effects. And then if you have insufficient pressure, then you get under damping, and you get this type of arterial curves. And a few examples, and then you need to know because it has come, I think actually it came in my exam many years ago in part 1. And they tell you, if you have a little blood clot at the tip of your arterial line, then you get an under damping effect. And that's false. You get an over damping because the wave becomes flatter. Another cause for example, over damping is, I want you to go to your hospitals on Monday and feel an arterial line. You know, not the thing that goes into the skin, but the cables to connect to the transducer. I want you to feel it, and you will see that it's harder than a normal IV line. And it's harder so that the pressure is not lost during the transmission of energy. But if you put an IV line, cable instead of arterial cable, IV lines are much softer. And then with this oscillation, the pressure will be lost in the system. And then you get an overdump effect. And reasons for underdamping instead are if you have gas or air bubbles in the system, they amplify the oscillations, and then you get an underdamping effect. So it's important that you know causes for overdamping, causes for underdamping. So if they list it in part 1 or they ask you in part 2, you can answer properly. Then we have the situation of what happens if my transducer is above the patient or below the patient. So if the transducer is above the patient, then for every 3 inches, then you get 6 millimeters of mercury less than true pressure. Because think, if my transducer is up here and I'm measuring the pressure, well, it takes much more effort to get to where the transducer is. So I get less than what I actually have. It's lost in the process. But if my transducer is below the patient, then you get much higher pressures because you're adding extra energy, like, for example, gravity. So it's important that the transducer is at heart level. Then we're briefly going to discuss pulse oximetry. Pulse oximetry uses the principle of photoplethysmography. It's a non-invasive method used to measure the proportional quantity of blood change using light absorption. You can use it in fingertips or in your earlobes because they have a higher blood flow, which facilitates the transfer. The device passes two wavelengths. So you see here, you have your two wavelengths here through the tissue being the finger, to a photodetector here, which measure the change in absorbance of each wavelength. So what happens is this. Carboxyhemoglobin and the oxyhemoglobin have different absorbances of light across different wavelengths. For example, at 660 nanometers, the oxyhemoglobin to oxyhemoglobin is maximized. So this is the oxy reduced. It's higher at 660. And instead, at 940, the oxyhemoglobin to the oxyhemoglobin ratio is maximized. So what happens is you get a recording on at which wavelength you have the maximum ratios. And then when they meet each other and you can measure those ratios, you get the value of the saturation. The pulse oximeter picks up an arterial component and a non-pulsatile component, and the ratio of these two at these wavelengths is determined. And then the ratio is then correlated to a hemoglobin oxygen saturation based on a calibration curve on healthy individuals. So what they did is basically they asked patients do not breathe, and they see how much they desaturated and how did the wavelengths perform. So that's why under 70% of oxygen saturation, then it's not too well validated, because this is validated in healthy individuals and it's not ethical to kill them in order to validate our equipment. So under 70%, the validation is not as good. But over 70%, there is a good correlation using to the hemoglobin oxygen saturation. And this article, if you want to scan the QR code, it has absolutely everything an anesthesiologist needs to know about the oxygen, the pulse oximeter. And it also includes this very nice table about the causes and mechanisms of unreliable oxygen saturation readings. And it talks about, for example, the metahemoglobinemia, the patients with sepsis shock, how does the fetal hemoglobin affects it, because there are other hemoglobins, not just oxy and desoxy, that can affect how the measurement of the wavelength. So what I've told you plus this table is enough for part 1 and part 2, but if you want to know more in depth, I highly suggest this article. And now, briefly, we're going to talk about the electrical safety. So, a body contact with two conductive materials at different voltages may complete a circuit, and this results in electrical shock. Everything leaks, even your phone, everything leaks an amount of current. And the severity of the electrical shock is determined by that amount of current. Of course, the duration also. So what happens is that the leaks are usually imperceptible to touch because skin has a very high resistance. So doesn't affect the heart. But our patients, the skin is broken. They have a surgical opening in the belly of 20 centimeters. So if there are leaks and we don't have the protection from the skin, then they have the risk of electrocution. So if the current bypasses the high resistance offered by the skin or is applied directly to the heart, 100 microamperes may be fatal. And that is why the maximum leakage allowed in the operating room is 10 microamperes. And this has come in the exam, and this will come in the exam, because there are a lot of units and you need to know the differences. So, imperceptible to touch, less than 1 milliampere. Fibrillation threshold, 100 milliamperes with intact skin. Applied directly to the heart, 100 microamperes may be fatal, and that's why the maximum leakage allowed in the operating room is 10 microamperes. Then the hires of electricity are, of course, the fires, shock, and arrhythmias to the heart. And the high-risk patients are then those having surgeries in the thoracic cavity. Other factors affecting this are the patients with hypokalemia, acidosis, elevated catecholamines, so think of a septic patient, hypoxemia, and the presence of digitalis. Adult patients with cardiac arrhythmias can be electrocuted through the misuse of pacemakers if they are connected directly to the myocardium. And of course, babies are more susceptible to electric shock because they have a smaller mass and a lower body resistance. We use the surgical diathermies daily. They generate an ultra-high frequency and that passes through the small electrocautery tip through the patient and exit through the dispersal path. And what happens is, if the dispersal path is not fully attached, then there is not a big enough surface for that electricity to leave the body. If the surface is very small, then it will get hot and you get burns. Or if you put it over bony surfaces, you can get internal burns. Or if you put it on top of prosthesis and then the energy tries to leave by the prosthesis area, it can heat up the prosthesis and also cause a burn. So those are the risk of the surgical the diathermy. And finally, the risk of fire. The incidence is very low, 1 in 87,000 cases, but I do 40,000 surgeries in my hospital every year, so we're talking about 1 every 2 years. The fire triad is the fuel oxidizer and ignition source. And when the surgical site is above the xiphoid and the patient needs more than 30% surgery oxygen, the airway should be secure. So those ear, nose, and throat surgeons that says, well, it's just a little thing. If it's over 30% oxygen that the patient needs, the airway should be secure. And the most important action in case of fire is to remove the endotracheal tube. So if you see fire, the first thing, in the exam, you always get, acute problems in the operating room. And how do you fix them? Think always ABC. So this is A. You need to remove the plastic that's melting into the patient's airway from the patient. So take away the tube, put saline to put away the fires, and then start hand ventilating and then secure your airway. And of course, help is coming because help is always on the way. But that's the ABC in type of fire. The first thing is remove the melting tube from the patient airway. I hope you enjoy this lecture and that I can answer all your questions on anesthesia equipment that come in the exam. Thank you very much.